this is question 5 from the 2011 Matt. They've certainly written a lot in this question, so I've had to cut it across 2 sheets, so we're only seeing the first little bit here. An n by n grid consists of squares arranged in n rows and n columns. For example, a chessboard is an 8 by 8 grid. Let's call a semi-grid size n the lower left part of the n by n grid. Okay, that is the squares located on or below the grid's diagonal. Right, fair enough. So they just left out the top right bit of this grid. Let us suppose that a robot is located in the lower left corner of the grid. The robot can only move up or right. Its goal is to reach one of the goal squares. Right, so this is Pascal's triangle, which are all located on the semi-grid's diagonal. In the example shown in figure C, the robot is in that square denoted with an R. Goal squares are grey. Let's call a solution a sequence of the robot's moves that leads the robot from the location to a goal square. Okay, write down all 8 solutions for a robot on semi-grid of size 4. So this is the thing. I mean, we know with Pascal's triangle, so we're going to get one possible route there, 3 there, 3 there, 1 there. That's how it all comes together, because we're just doing our binomial choices. We've got a choice of 2 options at every junction. So we're going to get 8 solutions, as it says in the question, because of that. So we could do right, right, right. We could do right, right, up, and right, up, right, or up, right, right. So I mean, that's the one that gets us to the 1 down here. Then we got the 3 getting to that 3. To get to the next 3, we could go right, up, up. We could go up, right, up, or we could go up, up, right. And then to get to the top one, we have to go up, up, up. So that's those. Devise a concise way of representing the possible journeys, what I just have, of the robot in a semi-grid of size n. Devise a, well, yeah. In your notation, which of the journeys are solutions? Devise a concise way. Are they asking for something else, or they just want me to use R's and U's? Devise a concise way of representing the possible journeys of a robot in a semi-grid. Well, I would say this is a concise way. So I think I've already done that. If they want something else, I don't really know what they're asking for. In your notation, which of the journeys are solutions? Well, all of them. Yeah, I'm not really sure what they're getting at here in this question. Which of the journeys are solutions? So we've got a string of, I mean, do they want us to say it has to be length 3 in this case? Maybe that's what it is. And this is for a grid, a semi-grid of size 4. Maybe that's what they want. I don't know. R equals right. U equals up. Solution equals n minus 1 length string. Yeah, string of R's and U's of length n minus 1. I don't know if that's what they're asking for. It's not really a very clear question, that, but that's all I've really got to offer. If you can think of something else, then let me know. Right, the rest of the question, because yeah, they've written so much here. Write down a formula for the number of possible solutions in a semi-grid of size n. Explain why your formula is correct. Right, seriously? Right, okay, so, well, we know it is 2 to the n minus 1 because we've got n minus 1 steps with 2 choices at each step. Okay, so this is not blowing me away, this question at the moment. Now let us change the problem slightly and redefine a goal square as any square that can be described as follows. A lower left square is not a goal square. Each square that is located immediately above or to the right of a non-goal square is a goal square. Each square is located immediately above or immediately to the right of a goal square is a non-goal square. Right, so we're turning it into an actual checkerboard then. So we don't have a goal square there, and then those 2, because they're up and to the right of a non-goal square, will be a goal square. Then we're going to get another diagonal of non-goal squares. Then we'll get a whole load of goal squares coming in again. So we're turning it into a black versus white chessboard. Furthermore, let us assume that upon reaching a goal square, the robot may decide to stop or to continue moving, providing there are more allowed moves. Right, so you could stop at one of these intermediate goals or carry on to one of the next lot. With these modifications in place, write down all the solutions in a semigrid of size 4 and all the solutions in a semigrid of size 5. So this is size 4, where we know the options for getting to the end. So they were the 8 that we wrote down, but now we just got 2 more. So we've got the previous 8 plus we could just do an R and we could do a U. So we've now got 10 solutions for that one. Right. Then what have we got? The semigrid of size 5. So for size 5, we'll be adding on another diagonal, which have got no more goals on them. So that'd be exactly the same. So that is the same for n equals 5 because, oh, they haven't actually asked for a justification. But anyway, because no new goal squares added. Right, it's taken longer to read the question to actually do it on here. We've only got one bit left. How many solutions are there now in a semigrid of size n where n is a positive integer? You may wish to consider separately the cases where n is even or odd. Well, we know that if it's odd, then it's the same as the even that is one less. So we got that for starters. So if n is odd, then the number of solutions is that for n minus 1. So that's dealt with that. So then we've got if n is even. So what are we getting if n is even? We're going to be getting, well, we're counting up because we don't know how big n is going to be. So, well, we need to make it even first of all. So then let n equal 2k. So that's made n even. Now we've got this 2k. So we know that we've got solutions here for, so we're going to have 2k as we're counting up in k, and we're getting these diagonals. So say we were, let's just think about it. Say k was 3, say we had that. So we were doing n is 6. So we'd have the number of solutions for getting to k is 1. So we'd have 2 to the, well, n is 2k, so that'd be 2 to the 1. Then we'd have the number of solutions to get to this one, which is 2 to the 3. Then we'd have the number of solutions to get to the next one, which is 2 to the 5. So that's what we have. So as we're adding these up then, as we're increasing, this is what we're getting. So we're getting the sum of 2k, these are all 2k minus 1s that we've got along here. We're adding up this. This is what we're adding up. So what does that mean then? So we've got the sum from, well, let's say I, because we've used n and k. So I is 1 up to k of 2 to the 2k minus 1. So, well, I now, 2i minus 1. Okay, so let's get rid of that minus 1 then, because that's just a half. Say a half of the sum of I equals 1 to k of 2 to the 2i. Okay, and let's simplify that even further. Well, I say simplify, it depends how you want to look at it, but in terms of adding up the sequence, I think this is going to make more sense. I'll make that a 4 to the I. So that's what we want to add up. So that is a geometric sequence because we're multiplying by 4 each time. So that is going to be equal to a half multiplied by, so our A is 4, that's our first term. Then we want to have 4, because that's our multiple, to the power of k minus 1 divided by 4 minus 1. Right, that is the sum of that. Yeah, that's fine. That's just a geometric sequence. So what is that giving us? That's giving us, well, 2 by the time we do the 4 times the half divided by 3. So 2/3 of 4 to the k minus 1. Okay. So what is that then? So that is our How many solutions are there now in a semi-grid for size n where n is a positive integer? You may wish to consider the cases where n is odd or even. Right, so we need to get this back into n then. So in this case, k is n over 2, so we can square root that 4 back down to being a 2 again. So 2/3 of 2 to the n minus 1. So that's what we've got for n is even in this case. So that is n is even. And then, as we say with this, so this is for n is odd. If n is odd, we do this for n minus 1. So that would be 2/3 of 2 to the n minus 1 minus 1. Because that will then take us down to the previous even number and give us that answer. Right, yeah, that's fine. Okay, it got a little bit meatier at the end, but even that was just adding up a geometric sequence. Again, with these sequences, you know, I always set out, I just start building it up rather than trying to completely abstract it. I suppose I could have just come in at this up here. You know, clearly a lot came back to this, so I've got 4 arrows pointing at it now. Maybe you could have just jumped in there and looked at it abstractly, but I always like to actually see what's happening by just building these things up. Because as soon as you get this pattern of the powers, then it makes the geometric sequence really easy to see. I didn't think much of that question really. The first first 4 parts were just, I don't know, they just seemed a bit confused, and I'm still not entirely sure that the second part have done what they wanted, but they should make their question a bit clearer, I think, in this one. It just wasn't, I don't know, it was just a bit off all the way through. But still, another one out the way.